Hello, everybody. We're Project D Group 72, Eric, Frank, Satya, and Chen.
Our project primarily dealt with the Johns Hopkins data consisting of daily counts of deaths and confirmed cases of COVID-19. We narrowed our focus specifically down to predict US confirmed cases across 3,043 counties and 49 states. We used data from January 22nd through May 3rd, holding out the final 7 days for prediction and validation. In addition to prediction, we gathered data on quarantine orders issued at the state and county level in an attempt to analyze their impact on prediction.
We ran variety of clustering like k-mean and dbScan. Finally ended up plotting confirmed cases proportion for each county on the map, which clearly explains how the cases are distributed across different counties indicated by color and size, where band green to red indicates low to high. We animated the map by day to analyze the cluster emerged over time. Biggest finding of the EDA is that few counties make up the vast majority of confirmed cases, especially New York City.
We started from the second-degree polynomial regression as the baseline model, and then moved on to support vector regression. We used parameters that were optimized using total US daily confirmed cases because running on a county level basis took a long time. We then explored separate approaches such as Facebook time series profit model and RNN. For time series profit, we tried to predict 7 predictions for each county without considering lockdown data. We were only able to run county level lockdown data for a small number of counties due to time constraints for exploring whether lockdown orders are effective on selected counties.
Both of the following GRUs use time difference data, meaning we fed them the growth in cases by day as opposed to raw count. We tried a univariate model where all time series were fed at the same time, meaning the model took in all counties at once in parallel, spitting out all forecasts at once, 7 predictions for each county. We then tried using state-level quarantine order data in 2 different representations/architectures to build the models.
With the LSTM model, we tried to include lat, long, and population to see how location proximity between counties and population density of each county impacts prediction from model. Data pre-processing includes all the counties with running 7-day time frame serialized by repeating the geo and population information before feeding to the model. All observations are fed into the model all at once for a training with a batch size of 1,000. These are aggregated prediction produced at a county level for each model versus actuals. We see that GRU models were substantially more accurate at the aggregated level.
And these are just 4 counties selected for display. Predictably, results fluctuated much more at the county level. We will see that the GRU appeared to perform best overall, but that the GRU sometimes really fell apart for counties where cases were low. Here in the top right is a county where the data was all zeros, yet the RNNs all produced positive numbers, possibly because the models were biased to learning on the high volume counties.
We listed out the MSE for each model as a basic comparison of model performance. And by drilling down to the county level, we realized the MSE is dominated by a large number of confirmed cases. Combining with the total US and selected county prediction, we conclude that RNN outperformed other models in most cases. Quarantine orders had an impact on prediction, but it was inconclusive. Based on our models, lockdown information doesn't appear to be a reliable indicator by itself. Other factors are probably contributing.
Similar to PCA, we took confirmed data and grouped it down to 2 channels, thus generating X and Y values for each county's COVID spread. This is TSNE grouping. Then on top of this, we colored each point with its demographic information determined by k-means clustering on the specific demographics, income, age, and race. As you can see, more than a few groupings of color appeared layered together in the TSNE plot. Thus, we conclude that these parameters may indeed be a good indicator of relationships between the spread of COVID-19 and demographics. While we found this relationship during our EDA portion, we couldn't integrate this into the model due to time constraints. Integrating both time series and non-time series dependent data proved to be a little bit more challenging than we had first thought.